psychological AI. So it is based on the insight that in situations under uncertainty, you need to make it simple, not too simple, as Einstein said, but you need to scale it down. And that was the original idea of Herbert Simon, namely to find out how experts deal with uncertainty and program this into software and then use it to make computers smart. That psychological AI had not worked as Simon thought, for beating the chess master. That was done by machine learning, which is blind with no theory and just computational power. But chess is a situation of an enormously stable world, and that it's not where psychological AI functions. The human brain evolved to deal with uncertainty, with a changing dynamic world, not with a stable world of calculable risk. So I will give you now two examples. One from a pandemic and the other one from our work with the Bank of England, that illustrate in both cases, we take what is known in psychology, how people deal with uncertain worlds, and then program it into software, and then make predictions. And I'll start with predicting the flu. As most of you will know, Google started in the year 2008 to make predictions about the flu-related doctor visits. And the idea was smart, namely, so people who have symptoms are likely to give in search terms that relate to the flu in order to find out what I should do. So the idea was one can very quickly and faster than the Center for Disease, the CDC, it can make predictions about the spread of the flu. And so what happened is, it worked first, but then in 2009, the swine flu came. And the swine flu came out of the season, and big data had learned that the flu is high in the winter and low in the summer, when the swine flu came in the summer, so it failed. At this time, the Google engineers had to make a decision, namely, how to revise the algorithm that didn't work well. And again, there are two ways to go. One is, it's a complex problem, so make it more complex. And that's where they went. So the original algorithm was validated on some 50 million search terms, and millions of algorithms have been tried. And it had some 45 variables, predictors. And that was then changed into a more complex algorithm with 160 or so predictors. The exact number of predictors is secret, and so is the algorithm, and so is the kind of predictors. So what we did is, we started from psychology, not from data. We know from psychological research that people, the moment they are in a volatile environment where quick changes are possible, they do not rely on all the past experience or all the data they have for the last years, but they rely only on the most recent data. So we formulated a heuristic that's very similar to the one you have seen, a recency heuristic that predicts that the flu-related doctor visits next week will be the same as those last week and ignores everything else. So I'll show you now how this heuristic fares. So what you see here are the years 2007 till 2006, and this was the time when Google Flu Trends was terminated. And the black line are the actual flu-related doctor visits. And the recency heuristic is the blue line, and the red one, Google flu trends. So you can see here in the year 2007, when it started, the recency heuristic is basically, the blue line is on top of the black one, so you can hardly see them. And Google flu trends does quite well. It's a little bit low. And in the early 2008, it's a little bit below, yes. But if you now go down here and into 2009, you see that the red line is going down, just it did last year, because the big data algorithm thinks that this year will be like the last year's. And that was the swine flu, that belly. Yeah? The recency heuristic can easily follow up all the changes very quickly. It's too late a week, yes, that is error. And then here is where the Google engineers updated their algorithm, as I explained before. They tried to make it more complex. So the Chris Anderson, editor-in-chief of Wired, announced around this time that using big data and Google flu trends, that correlations supersedes causation and science can advance even without coherent model. And he asked, what can science learn from Google? Let me pose a different question. What can Google learn from science? And that's one thing that Google can learn from science. If you're dealing with uncertainty, make it simpler. But the Google engineers made it more complex here. And you can see that we have checked that it didn't make anything better, making it more complex. Here it started to overestimate, and here it ended up overestimating very highly, and at the end it was shut down. If you look at the entire time of 8 years, the error that Google flu trends made, that's on this scale here, is 0.38 percentage points. The recency heuristic could reduce the error to almost half. This is an example for one data point can predict the flu better than big data. And the reason is because we have to do with a volatile world. Here I give you another example, and to my great pleasure, a group of economists have now realized about the power of simple heuristic, as we call them, fast and frugal heuristic. And this group of economists, including a Nobel laureate, Joseph Stiglitz, have tested exactly the same recency heuristic on a different problem, on predicting expectations in markets, demand expectations. And the conclusion was that in complex and changing macroeconomic environments, fast and frugal, robust heuristics may not be second best options as economists have believed, but rather rational responses. So my final example is about our work with the Bank of England, and I will use it to explain a different kind of heuristic. So one of the things that went wrong with the crisis were the algorithms being used. And predicting the financial world is most of the time predictions under uncertainty. And I'll invite you to read Andy Haldane, who is the chief economist of the Bank of England, his article, The Dog and the Frisbee. The Dog and the Frisbee is named after the gaze heuristic I showed at the beginning. That was the first heuristic explained him, and which he then used to go and give a Jackson Hole talk that was unheard of with this title and got the prize of the best speech from Wall Street Journal. So I'll show you one of the problems. The problem is how to predict which bank is volatile, that may fail and may need to be saved. Current models are highly complex, and we work with the Bank of England to construct fast and frugal tree. This is no longer a single reason heuristic. Here are three: the leverage ratio, market-based capital ratio, and loan to deposit ratio. I'm not going into details, but I want to briefly explain you how such trees are built. And they are built by a combination of expert knowledge or intuition and lots of data. So the reasons were extracted from the expert judgment of the economists on the Bank of England, the top. And they consider leverage ratio, market capitalization, these are the most important reasons. The structure of the tree was our contribution. It's called a fast and frugal tree. It's an incomplete tree. And it's incomplete in order to avoid overfitting the data. And it has the following property. In the case of binary decisions as here, it has the number of exits. There's an exit after every question. And the total number is n, the number of questions, plus 1. And the values, the cutoff values, are then estimated again from data. So that's an interplay in that. So for instance, if this fast and frugal tree would have been used before 2008, UBS, one of the banks that had been saved, would have been immediately put in red flag because their leverage ratio were much smaller than this limit. Also note that the tree is not compensatory. You cannot make up, UBS would have met all other criteria, but not this one. So it's not compensatory. It's not like expected utility maximization. We always can make trade-offs. It's more like the human body. So if your heart fails, your vision and your lung doesn't help very much, even if it's good. So that's the idea. And that tree has been shown to be competitive with more complex models and typically better, and also it's transparent. And that's an important advantage.